Мой доклад о криптографических уязвимостях.
I will make a presentation about zero knowledge proof, cryptographic vulnerabilities. Plonk. What's Plonk? Plonk is the proof which allows a certain determined program to prove the set of its input, output, and intermediate variables without actually disclosing this set of variables. Some of the variables may be fixed. There may be different types of variables, input, output, variables. And as an example, I would like to show you the proof of knowledge of the hash function. So you can prove that you know the string of which hash function equals a certain number without actually disclosing this string. This program works as an arithmetic scheme which has n nodes. Each of the nodes has two inputs and one output. Between them, the certain ratio is performed expressed by this formula. QL and QR are coefficients with the input left and input right. QM is the median. QO is the coefficient on the output, and QC is the coefficient with 1. For example, with the second node, the coefficient of QL is the coefficient with 0, QR with B2, QR equals 2. It's the second line here in this chart. QR with the constant equals 3. QR on output minus 1, Q output is minus 1, and QM equals 0 here. Apart from the ratio inside, we need to also code the equality of different elements between the nodes. Normally, they are outputs of one node that are input for another one. For this, we have all of the operations performed in the certain field. It has a multiplicator group with the H group in it. The element that creates it is in the power of n. So if we don't find this element, we select the element with the minimal order, which exceeds the number of the nodes in the scheme. The H subgroup is used to index the nodes and left inputs. It has two classes that are used to index the right inputs and outputs. Here in this chart, the equality between inputs and outputs are expressed in SA, SB, and SC. The elements that are not touched upon with these ratios are highlighted in white. For example, in SA column, we have element 1 and G squared. The element which equals A2 is put with the element which corresponds C1. This is the first element in the final column. And instead of it, there is an element, the first element of the first class. The same occurs when we move the element which is responsible for C2 and the element which is responsible for B3.
Итак, у схемы есть следующая компонента.
This scheme has the following components: the number of nodes, selectors,
В ходе предобработки
and if you do the pre-processing, all of the selectors, you put those expressions that are in the point which corresponds each and every node
группы H
in the age group. They are expressed with a value which equals to this number.
Многочлен L, например, от X
So it is equal,
значение равное единице в точке 1,
which is 0 in point 1, 0 in G squared,
многочлен QR принимает значение равное единице,
and it is equal in the position
единицы в точке G в квадрате.
G squared.
Ну, то же самое, потому что принцип устроится многочлены для подстановок.
The same thing applies for polynomial function elsewhere.
Так, на вход протоколу Plonk подаются
we feed
подаются входы, которые задаются
the inputs that are
считаются
setting up the scheme, and they're considered to be of a multiple use. So we can obviously use them with different set of open variables.
Разными выполняющими наборами, но схема при этом остается неизменной.
But the scheme remains unchanged.
Другие, так, ну да, это многочлены, это n.
And these polynomis for selectors, and they are polynomis.
Открытый вход, public input.
Other polynomis. Public input
фиксированные переменные, которым
are fixed
наш выполняющий набор.
Variables that should be there in the set of data. And here's the reference string. It's the base point of the elliptic curve, which is multiplied by certain numbers of x, and the x is secret, and it's killed straight after this string is formed. So no the prover, nor the inspector knows. It proves the knowledge of that.
Что доказывающий знает,
that the one who proves knows the coefficients of the defined polynomial. For instance, they need to calculate.
Ему нужно получить точку на
They need to get the point on the elliptic curve, which equals the
значение некоторого многочлена в
the value of a certain polynomial in the x point. And they don't know the x point. The only way to do that is to come up with a reference string in the polynomial. It's called a commitment, and it proves, first of all, that they know the coefficients of the polynomial, and second of all, it proves that this polynomial is possible to be set up. So this polynomial
ну, допустим, не является...
Imagine that this one does not contain any irrational coefficients,
ну, или чего-нибудь такого.
Or something like that.
У доказывающего
the prover
есть свой секретный от всех код.
Has its own secret code. It's a witness. It's this, the knowledge that it proves. And the inspector
commitmenты для всех
has commitment
многочленов соответствующих
for all of the polynomials that meet the scheme.
Итак, основные цели доказательства
So
доказать
we prove that it actually meets the public input of the selector scheme. For this,
такая промежуточная задача это доказать
an intermediary task exists that you need to meet the polynomials in a random point, the commitment. And in some situations, it may become very critical to prove that the public input parameter is substitute.
Итак, первая задача
So the first task is to prove that the selectors meet the public input. You know that for selectors,
входов и выходов у нас должно
for the input and output, we need to run the following
Я, к сожалению, не могу его показать.
ratio. I cannot show it to you right now, but it's the equation.
Из всех написанных здесь.
It's on the left-hand side.
У нас есть многочлены, которые
We have polynomies.
соответствующие некоему.
So in any point that refers to a node, give the value of the selector in this point. In the first round, the prover uses exactly the same polynomies for inputs and outputs.
X, B от X и C от X.
A, X, B, X, C, X, and they measure their commitments in the C small.
В третьем раунде он
In the third round,
многочлен, ну,
they create a polynomial,
собой,
which is the representation,
представляющий собой вот это вот уравнение.
which is the representation of the equation on the right.
И так как каждый из членов из перемножаемых здесь многочленов,
As of all of the polynomials multiplied here gets the value of a selector or input or output, and at a certain point it is expected that this polynomial will be equal 0 in all of the points
соответствующих узлам нашей схемы.
of the neighboring scheme.
Доказывающий может это
So, how the prover can prove that? They form a polynomial that are equal 0
во всех узлах схемы. Это
in
обнуляющий
all of the
многочлен.
nodes of the scheme. It's the ZHX up there in the round 1 section.
Делит ЕКО от X.
It divides it by ZHX.
Ну, в случае, если все составлено верно.
So if everything works and if the prover is honest, EQ from X is divided by Z at by X, and the prover can come up with a commitment for this number. On the contrary,
ЕКО от X на
if EQ from X is not divided by X, the commitment becomes impossible here.
Так. Вот.
So,
каждом из многочленов от X
in each of the polynomials from X,
это
the first part is the
некоторый случайный многочлен, домноженный
polynomial, a random polynomial, which is multiplied by ZH from X, and it does not influence the calculation, yet here it allows to hide the values of the witness elements.
Даже если
So even if the attacker
получит возможность перебрать
will get a chance to run through all of the values, they won't be able to say which one is the real one.
Так. И первая уязвимость.
And the first vulnerability here, which we'll cover here today, is the absence of the camouflaging polynomials. So on the right-hand side, we are showing how we can fix that by adding such polynomials. It could not be exploited, of course, but conceptually, there is such a vulnerability.
Что касается public input,
as far as public input,
может закладываться в
the correction for public input is expressed here as we generate it from the scheme. It somehow violates the principle of the
между
division
и
of the
компонентами доказать.
Disposable and non-disposable components, but it works like this.
Соответствие назначения и постановкам.
As far as the values correspond the substitutes, for example, we would like to prove that some of the
Как мы можем это сделать, если у нас
volumes are equal? How do we prove this if there is no such definition
то есть в данном случае
in existence? We can index them. First of all, we use A1, A2 with the witness components.
После чего с помощью случайных
After that, with the use of the random values of beta,
это к произведению.
we can do the multiplication.
То
If our volumes are equal,
то собственно, самая нижняя левая
you can see there on the left lower corner, there's the equation which will be resolved. And the contrary is wrong, but the one who proves this does not manipulate the random values of beta, and we will speak about that later, and they will not be able to select them,
чтобы доказать
to prove
вероятность этого крайне мала.
that correct. There's a very low chance that it may so happen.
Получается переменная
In the third round, we have beta and gamma as variables, and we come up with a polynomial
который полностью соответствует тому же, что
which completely matches exactly what we have there under the multiplication.
z от x у нас в точке
Polynomial z by x,
g
g squared,
и так далее.
etc. So in the g,
n плюс 1 он будет
in the power of n plus 1, it will also be equal 1.
И ну, как легко видеть, он
So as far as you can see,
что
here it has the features
результат домножается на ρ.
that each time the result is multiplied by rho rg in the power of 3. We cannot just provide the commitment from 1. We need to prove
Во-первых,
that first of all,
z
z from g equals 1,
и во-вторых, что корректны все шаги
zg equals 1, and all of these steps
g в степени n.
of zg in the n in the power of n are correct. So therefore, in the third round, we come back to this polynomial, and the second component here is responsible for the second part of this proof, and the third component is responsible for the first one. In the second component, we see that zx minus
z от x
zx xg
в общем, домноженное на f от
multiplied by f of x and qrx,
обнуляется.
they are equals 0.
Мы можем
They are equal 0.
получить
We again can get the commitment from that number if everything is divided by zhx.
Commitment для
So the commitment
разбивается на три части
is split into 3 parts
в целях оптимизации.
to optimize it, for optimization.
Так, соответствие значений в случайной точке коммитментам, то есть evaluation.
So
проверяющий
whether the values meet the random
число
commitment point,
не
evaluation
знает
proof. So they don't know the
не обладает возможностью
witness,
выполнять
they don't know
слишком сложное вычисление.
how to do the complicated and complex calculations.
Мы должны предоставить ему
So therefore, we need to provide them a chance to somehow very easily check
то, что все эти значения были сформированы.
that all of these values were
И для этого
formed in a proper way. For this, we use evaluations.
доказывающий предоставляет значение.
And the one who proves provides all the
Он отправлял в некое
polynomies to a random z point. So the polynomial zg and zg point, which is very important for the proof. Then they combine a linear polynomial.
При перемножении нескольких многочленов
If we multiply a few polynomials,
никак не меняется. Часть из этих многочленов можно
there is no difference. Some of these polynomials can be replaced by their evaluations,
их 2, 3 и так далее.
where there are 2 or 3 of them.
Для значения RATX тоже считается evaluation и точно так же присоединяется.
And the same applies to the proof.
После чего необходимо доказать
After that, you just need to prove
самые evaluations и commitments
that these evaluations and commitments
одному и тому же числу.
actually meet the same number.
С помощью теоремы Безо.
It's done with the Bezo theorem.
F от x минус f от z
fx minus z divided by x minus z.
Ну, для этого доказательства строится
For this, the proof contains polynomial zeta x,
в которых из всех этих многочленов мы
with all of these polynomials we extract their evaluations and we divide them by x minus
опять же помним, что не сможем
beta. But we cannot come up with a commitment for this number if they are not divided.
Ну и, наверное, многих тут волнует.
Maybe you would like to find out if the tester does not know A, B, C, they don't know anything, so
просто какую-нибудь ерунду.
Maybe they will be just sending random rubbish.
Выбирает случайный A от X, B от X и
They select random
также случайные Z
from
от X
X,
и случайные
ZX.
На каждом этапе после
At each stage,
каких-то
after they add some
он обновляет
of
внутреннее
commitments,
состояние хэша губки.
they add sponge cache and they get new random variables out of that. Then all of the proof generated does not meet the public input. Therefore, if we did not initialize our sponge hash, it may simply come up with a new public input. In some of the applications, it's not that critical because it doesn't really matter which public input was there. So it's the knowledge of any set of data which is important there.
Он вычисляет public input.
It calculates public input and it sends to the inspector. This vulnerability called frozen heart was there in Dusk network. It allowed you to transfer an unlimited amount of money.
Тут показаны исправления этой самой уязвимости.
On the right-hand side, the corrections are shown.
Мы инициализируем транскрипт.
So we initialize the transcript with the public input.
Да, то есть если уже изначально транскрипт будет зависеть от public input,
if this transcript will depend on the public input, we will not be able to replace public input, because for this we'll have to break this hash function.
Ну и немного о том, как проверяется доказательство.
So how do we check this proof?
Проверяется с помощью...
It is checked with a bilinear function. For this we use the veil coupling, which shows a couple of elliptic points on the curve as an element of the end field. This veil coupling should have the following properties that are shown on the right. If it itself equals 1, it should be bilinear. The amount of the couples equals the multiplication by all of the arguments. So, as far as the bilinear expression is, the multiplied coefficient with all of the arguments should be expressed as stepping coupling.
Если ни одна из точек там не является
if none of the points is the combination, the coupling should not be equal 1.
Ну и также важно существование эффективного алгоритма вычисления.
And it's important that we have a very proper algorithms of this coupling. So these points will be expressed with the indexes, with the square parentheses, square brackets.
Проверка доказательства осуществляется...
How do we do the check of the proof? We compare the two veil couplings.
То есть теперь мы переходим к...
So now we move to the lower part of the slide.
Проверки.
And as we do the inspection, the
Сначала с помощью доказательства
with the proof of the public input, they generate random variables, beta, gamma, alpha, zeta, v, and u,
из общего
that they get from the
затем
the proof.
Строит собственноручно обнуляющий многочлен.
Then they do build the polynomial, the Lagrange coefficients, and the polynomial for public input.
Затем с помощью этих
Then with the use of these polynomials and the commitments, they will build the analog of T and R polynomials. So in other words, they repeat the T with the exception of one simple optimization. With the use of them, they come up with E and F.
Будут являться суммой числителей
will be equal to the sum of the numerators of WZ
с коэффициентом O.
With the coefficient O, coefficient U rather. And how do we check the coupling? It actually corresponds with the confirmation that omega zeta multiplied by O multiplied by omega zeta G multiplied by X minus zeta G equals the difference between F and E.
Так. И на заключительном этапе
And in the final stage, as we check this proof,
там тоже могут скрываться уязвимости.
there may also be vulnerabilities hiding, and some of these vulnerabilities is zero block one stack block verifier.
Заключался этот баг в том, что если отправить
That's a bug, stack block verifier. If you send instead of omega z and omega zg, I'm sorry, instead of wz and wzg, if you send a curve on the infinity, the proof will be tested. But ideally, this should not be happening, because if this commitment from F does not equal commitment of E,
их разность не будет равняться точке на B.
And the difference between them is not equal the point on the infinity point.
Спаривание Вейли соответствующее не будет.
The Weyl coupling is not equal 1. And it has become possible through a number of errors. First of all, the verifier continues work if the points do not belong to the elliptic curve, but it only excludes them from the following operations, following calculations. So we are talking about the absence of the test of the input data, to which a lot of time was spent in the previous presentation. So as with the upcoming test, the O point is not the point on the infinity. Different codings are used here, and the O point is sent to a different code. Then for the inversion of the P number, a method is used, which is based upon a small Fermat theorem, when we do not check the input data for their correctness. So therefore, it's possible to calculate the reverse number for 0. 0 in the p minus 2 power equals 0 as well. Number 4, before you check the Weyl coupling, you transfer it from projective coordinates to affinic coordinates. It happens with the package normalization, during which the E1 non-zero point, E1 1 minus 1 also becomes 0 point, and the final check is all about checking the coupling between the infinity point and the second base point of the elliptic curve. According to the verifier logic, if this point does not lie on the curve and it's not the curve on the infinity, in accordance to the second verification, its coupling to any point equals 1. So thanks to this independent and very unprobable errors, we were able to exploit this vulnerability.
Насколько известно, никогда не использовалась.
It never was changed.
Товарищ, который ее нашел, сразу же опубликовал.
The person who found it
по ней статью.
Found an article about that.
Ну, собственно, все на сегодня. Спасибо за.
So basically, this is it. Thank you very much for your attention.
Верно ли, что на первом раунде мы с помощью полиномов проверяем, являются ли два массива значений перестановками одного и того же набора? Но это происходит не в первом раунде, это происходит частично во втором, частично в третьем, но, в общем-то, да. Ну, скажем, при применении...
So imagine that we use the...
Остаются ли элементы этого массива неизменными?
Second question, whether the elements of this volume remain intact.
Равенство между элементами.
So you check the equality between the elements.
What
are the perspectives of the use of the machine learning and AI to eradicate vulnerabilities in zero-knowledge proof, and what are the potential risks with this approach?
Трудно ответить на этот вопрос.
Well, it's very hard to answer this question. I think most of the vulnerabilities,
как уязвимость арифметических схем или
whether
какие-то стандартные уязвимости,
there are standard vulnerabilities like frozen hearts, they may be there with the machine learning.
А вот о рисках такого,
But as far as the risks are concerned,
не знаю, наверное, я ничего не могу сказать.
I don't really know. I don't know much about it.
Так, есть ли какие-нибудь интересные еще баги?
Are there any other interesting bugs?
В блонках я, в принципе, про все самое интересное рассказала.
I explained the most interesting ones about Plonks. There are interesting bugs in the arithmetic schemes. I mentioned them previously.
Ну, в других видах снарков тоже встречаются интересные баги.
We may also see other interesting bugs as well.
Так, где используется этот протокол?
Where do you use this protocol?
Ну, например, в Dusk Network, WhatStack.
It's in the Dusk Network, WhatStack.
Так, как отлавливать такие...
Okay, how do we search for such errors?
Мне кажется, в общем случае нужно исходить из
We basically
того, что
need to
проверять все входные аргументы для всех функций.
We need to check all of the
принимать какие-то странные
all of the arguments that may be expressed in different values, strange values.
Следить за тем, чтобы
Then you just need to see that the protocol realization does not change much from the specification.
Маскирующих многочленов это вот из этой области.
So,
ну и, наверное, следить за, собственно, криптографическими исследованиями. То есть,
as for cryptographic research is concerned, you just need to track them as well, follow them when you detect the vulnerabilities in the protocol itself.